All right, so stole my own thunder with the cusp, but that's all right. A cusp, that's a cusp is when the function is continuous at c, so still looking for continuity. But, and in all cases, you should be looking for continuity because none of this stuff happens if the function isn't continuous to begin with. All right, you don't have to worry about differentiability because it wouldn't be differentiable at all to begin with. All right, so we're looking for the limit as x approaches your constant c from the left. I'm sorry, does that say from the right? What does it say on your page? From the, oh, I could go left first. All right, well, I'll take it as a typo. Some of you are.
Read's already on.
Yeah.
Read was like 10 seconds.
Let's one of type this one.
Yeah, but remember, once you max out, you max out, so.
How many?
I don't know how to
describe
describe this.
Already done, sorry.
3, once you hit your 3, you're done, so.
Well, I don't know if you've accepted.
Exactly, so what I say is, you know, just because you see somebody else putting it in, doesn't mean you shouldn't put it in yourself, because you never know. All right, so continuity.
Not worth the effort.
Now, in this case, you do see that there is a cusp here, and it is obvious from the graph. Analytically, if I was not given the graph, to know that there was a cusp there to begin with, that could be tricky. And we'll talk about how we determine that just from the equation tomorrow, but for now, we're just going to get into the concept. So I'm going to assume that it's happening here, because I have the visual. So I'm going to find first f of 0, which is 0, limit as x approaches 0 from the left of x to the 2/3 would have to be equal to the limit as x approaches 0. Why do I have a 1 there? Jeez, Monday morning. From the right of x to the 2/3. Now this isn't piecewise. This is direct substitution. So it doesn't matter if you plug it in from the left or from the right, you're going to get the same thing, and in both cases 0. So therefore it is continuous. So now I just need to test the limit. So what I need to find is, given f of x equals x to the 2/3, I need to find f prime of x. All right, so this is a little bit more of a doozy because you have to figure out the derivative first. Limit as x approaches a of x to the 2/3 minus a to the 2/3 over x minus a. Ooh. All right, so let's pause and ponder. I'm just going to re-explain this a little bit. That wasn't recording. So, and maybe it'll be helpful. We have difference of 2 cubes on the difference of 2 squares on the top. So we factor that using the difference of 2 squares technique. So the square root of each part, square root, and the square root of this guy, again, dividing the exponent by 2. So square root, make sure the signs are different. This guy, the x minus a, we're getting the factors, and actually, it's probably a good idea I'm going over it again, because we got this idea from Algebra 1, Algebra 2. Then we learned how we could expand it maybe in pre-calc, but definitely in here. And so the idea is we're following this model in order to come up with the factors. Now, the reality is you can just copy it from the work we did a couple pages back, but the idea for real is that you're taking the first term and taking the cube root of it, the second term and taking the cube root of that. So cube root, square, multiply the 2 together. So x to the 1/3, a to the 1/3, square. So a to the 1/3 plus a to the 2/3. So that gets rid of this guy. And that's the one that has to go, because that's what's making the bottom undefined. at this point, maybe you're not ready to skip steps. So I won't just yet. We're going to rewrite, so we're going to apply the limit, because once troublemaker's gone, we can apply the limit without worrying about getting undefined, unless it's supposed to be like infinite situation. I'll take it here, because I'll forget. Thanks, bud. All right, so I'll write x to the 1/3, x to the 1/3. Sum of the two terms. Over x to the 2/3 plus x to the 1/3, not an a, an x to the 1/3 plus x to the 2/3. All right. The idea being that hopefully sometime down the line this will be a step that you can skip, if it's not already. Could be. So we have 2 of those x to the 1/3 on top. On the bottom, if I keep the base and add the exponents, that middle term also becomes an x to the 2/3. So I'm gonna have 3 of those x to the 2/3. So then I can simplify and I could look at it a couple of different ways. I could have a negative exponent if I want, but if at some point I'm going to apply a limit, I might want to have it so that it's in terms of positive exponents. So I'll do the keep the base and subtract the exponents, but I'll bring the result to the bottom. So I'll do bottom minus top. So 2 over 3x to the 1/3. That's actually, I don't want to say shockingly simple of an answer, not the process, but based on the work that we had to do, that's pretty surprising that it actually came out to be that nice. Unless you know the power rule for derivatives. If you do, then you knew that like a day ago. Anyway, so what I want to do here, because we found continuity in the first step, then we embarked on the journey to determine whether or not that this was a cusp. Reality is we already knew it was a cusp, we need to prove it. So what I need to do is find the left and right hand side limits as x approaches whatever the x value is of the point of the cusp for that function, the derivative function. So I'm going to find the limit as x approaches 0 from the left of 2 over 3x to the 1/3. See what that is. The limit as x approaches 0 from the right of 2 over 3x to the 1/3. All right, in both cases we get something over 0. So in this case 2 over 0. Well, actually both cases 2 over 0. All right, so based on our knowledge of the function, we know that we're dealing with a vertical asymptote here. It's just a question of what's going on at that vertical asymptote. The limit approach has kind of verified for us that, yeah, we are dealing with a vertical asymptote, which means that these guys, you know, they're not going to be D and E. It's going to, well, not necessarily. Each one of them should be going to some kind of infinity, either positive or negative infinity. So at this point, you do one of two things. You can create the graph by hand, which wouldn't be too crazy if you had to do it by hand, you know, on the AP or something. Or you can just pop it into the calculator and take a quick look. The other approach would be to use just a test value or two, right? So something to kind of give you a sense of the direction. Something very close to 0 but left of it. Something very close to 0 but right of it, right? Ideally something relatively convenient so that you're not destroying yourself trying to figure it out without a calculator. This is kind of like the calculator approach without using a calculator. So it's a nice way of getting the credit, getting the answer without really going nuts over it. So I would take some small value, some value that's less than 0 but close to 0. That's also a perfect cube. So maybe I would try So test x equals -1/8. And then test x equals +1/8. Right? I just need to get a sense of the kind of infinity it's going to. So if it comes back with a positive answer, you know, a positively large answer, we can assume it's going to infinity. If it comes back with a negatively large answer, then we're probably going to negative infinity.
Would we do like -1 and 1, or would that be too big?
It's probably too far away where you wouldn't necessarily get the sense. I mean, ideally you'd do something like, I don't know, 1 over 729. It's a perfect cube, but not the nicest one to work with, I guess. You know, maybe split the difference and go like 1 over 64. You know, you don't want to take any chances with this on the AP. Or maybe you do, I don't know. We'll see. We'll see where we are in early May. Oh, so I don't need the limit anymore because I'm actually testing the value. So I find f prime of -1/8. Basically, I'm just settling for -1/8 just to keep the numbers nice. I'm not really in love with her. I'm just settling for her. -1/8. No, you're not the one for me. Hopefully I did that math right. -4/3. Cube change flip. And so we can assume, just based on math and stuff, that this would be +4/3. All right, so it's looking like it's trending towards negative infinity from the left side, positive infinity from the right side. Maybe you want to test another value to make sure, but if you know there's a cusp there already, then you could probably, you know, settle in on this. So what that's telling me as a conclusion statement is that this limit is going to negative infinity, this limit is going to positive infinity. And that's what the rule above is really trying to say. Let me zoom it back in. It's saying that on either side of your cusp, your two derivatives should have limits that are going to opposite infinities. All right, one should be going towards a positive infinity while the other goes to negative, or vice versa. If that's the case, we have justified the presence of a cusp. So it has to be continuous. You have to justify continuity first. Then after that, we have to address finding the derivative, which will be much easier in the coming days because we'll have shortcuts to this. You know, a shortcut that'll take all of this work and make it somewhat meaningless. You could get from here to your final answer in a step. Anyone who was in BC last year knows this. So, but, you know, in order to understand how a derivative works, this stuff is really important. All right. So, the next one, the vertical tangent case, we've already tackled this, and I took you through the entire approach really, except for the last step, which was addressing the limit component. So let me go grab that work real quick. All right, so this is all old stuff. Really all I needed here was the f prime of x equals this function, so this little guy here, and also the fact that it gave us undefined when we tried to plug in the 0. But aside from that, we didn't really need any of this, just the derivative is all I wanted. So what I need from this is a limit. So limit, I believe, let's see, yeah, the vertical tangent, if it exists, would be at 0. So as x approaches 0, from the left, of the derivative function, which I'm going to write as 1 over 3x to the 2/3. And I need the limit as x approaches 0 from the right of 1 over 3x to the positive 2/3. See if I can get rid of this real quick. It just looks too close to the 3. All right, so same idea. Here's a test value, but this one's much simpler.
Why are we using the same derivative when the function's different?
It's the same function on either side. It's not piecewise. So
The example says y equals x to the 1 third. So why are we using the same derivative?
I thought this was the same.
Vertical tangent. Are we just gonna pretend it says 2/3? Just change it.
No, I believe this is this. Oh, sorry. All right, so what I would want to do here is plug in a test value to demonstrate that it's going to the same kind of infinity. All right, so that's the important thing here. If you look at the rule, it's telling us that the two infinities should be the same. If it's going to positive infinity from the left, it should be going to positive infinity from the right. Right? If it's going to negative infinity from the left, it should be going negative infinity from the right. The good thing about this function is that there is no work to do. Because we know that there's a vertical asymptote at x equals 0 in this derivative function. Right? So at the bottom equal to 0 and solve, you get something equal to 0, x equals 0, specifically in this case. No matter what I plug in for x, what kind of number am I going to get as a result? A what? Positive number. All right, so since we know it's got to go to some kind of infinity, and it's always got to be positive no matter what I plug in, whether it's a negative number or a positive number, they must both be approaching positive infinity. All right. Also, you can kind of, cheating is not the right word, but it's sort of, yeah, you can intuit it. So if you're assuming that the slope, because again, that's what the derivative is the slope, is approaching some kind of infinity. Just take a ruler and trace along the path, the slope of the path. So adjust your slope, create tangent slopes as you shift the ruler closer and closer to whatever the point you think has a vertical tangent. All right, so you can see that the slope is getting more and more positive as I go this way. All right, now if I start over here and do the same thing, you can see the slope is getting more and more, the ruler is pitching upwards. The slope is getting more and more positive as I work from left to right. They're both going to the same kind of infinity. They're both going to positive infinity. All right, you can do the same thing with a cusp. Because again, we're just addressing slopes. So follow the curve from some extreme point and work your way towards the middle where you think that cusp is. You can see that the ruler is going in the downward direction. All right, so it's going towards negative infinity. Whereas from the right, it's pitching more upward, so it's going toward positive infinity. All right, so the ruler test can give you a sense of what the infinities ought to be so that you can kind of finagle the algebra to make it work. So when you get to this step here, you already know what kind of infinity it's supposed to be. Okay, so the test values become irrelevant, right, if you have a sense of the slopes. Right? And all you would need to do for some kind of justification there, because again, at this point it shifts over to being more of a graphical technique, just draw a few examples of what your tangent lines would look like along the curve coming in from the right, coming in from the left, just to demonstrate to the reader that it's going to whatever infinity that you claim it's going to. And then that's enough. So then you don't have to worry about plugging in these values. Although, if you recognize the nature of the function, then you realize that in this case, if I plug in a negative, I'm getting a negative. If I plug in a positive, I'm getting a positive. Right? And in the other case, because it was an even power, if I plug in a negative, I'm getting a positive. If I plug in a positive, I'm getting a positive. So, don't neglect the actual nature of the numbers too, because that could be a benefit also.